Okay, gentlemen, thank you for filling out the form. It's clear the videos are working and we're happy enough. But if we want a live lesson soon, let me know. Even if there's just a couple of you or one of you wants one, I'll do one. Okay. Now, I've already written the answers here, unfortunately, but the coordinates of x and y, so 7, we have this cubic graph. And you can see here it only crosses the x-axis once. So that means it's going to have one real root, but it needs to have 3 roots, so 2 will be complex. So the coordinates of the x and y intercepts are a, 0, so a is 2 because it's 2, 0, and 0, b, so b is negative 10, okay, because it's the y-intercept at minus 10. What's the value of the real root at f of z? It's z equals 2, okay, z equals 2, because that's where it crosses the x-axis. And then what's the value of k? Well, it crosses at minus 10, but you can see here it's actually minus k, so k is positive 10. And then the last question I'll be able to do here is z plus c is a linear polynomial and it divides f of z. Now, what will divide a function? Any of its factors. Okay, now this says it's a linear polynomial, so that means it's the factor coming from the linear root. So if z equals 2, z minus 2 is the factor. And that's h of z is z minus 2. Okay, it's that simple. Then find the non-real roots of f of z. Okay, so the non-real roots. So the first thing I need to do is to divide z minus 2 into z cubed plus z minus 10. Okay, I'll put 0z squared there. So z squared, I get z cubed minus 2z squared. Change the sign. I get 2z squared plus z. So plus 2z there. 2z squared minus 4z. Change the sign. 5z minus 10. So that's plus 5. So the factor which is going to create our complex roots is z squared plus 2z plus 5. Okay, that's the complex factor. That's the factor of the quadratic, which is this has 2 complex roots. So I want to find the roots. I'll let it equal 0 and I'll use minus b formula. So z is minus 2 plus or minus root 2 squared minus 4. Okay, so minus 2 plus or minus root 4 minus 20 over 2 minus 2 plus or minus root minus 16 over 2. So it's minus 2 plus or minus 4i over 2, which is minus 1 plus or minus 2i, and they are the 2 complex roots. Okay, so that's question 7. Now question 9. Very similar question. This is 2 integer roots, and you could say that it's a quartic, so it's the power 4, so there's be 4 roots. It has 2 integers, you can see there, at minus 1 and at 3. So the real roots, z equals minus 1 and z equals 3. So show that z squared minus 2z minus 3 is a factor. Okay, so show that's a factor. Well, I'll be able to show it's a factor because I have 2 real roots. Okay, so my real roots were minus 1 and 3. So I can either turn these into two factors and multiply them, and I'll get z squared minus 3z plus z minus 3, z squared minus 2z minus 3 equals 0. Okay, that'll show it's a factor. Okay, or you can do sum of the roots minus sum of the roots, so 3 and minus 1 is 2, so minus sum, minus 2, and then product of the roots, minus 1 by 3 is minus 3. Hence, find the two non-real roots. Again, same as the last question, I'm going to use minus b here to solve for z. Minus b is plus 2, plus or minus root, minus 2 squared, minus 4 by 1 by minus 3, over 2 by 1, 2 plus or minus root 4 minus 12 plus 12. No, where have we gone wrong there? Over 2. I've gone wrong because this is going to give me the real roots again. Apologies. So that was the real roots. So these give it the real roots. So I realize it's going wrong there. So if I divide this into the original polynomial, which is z to the 4 minus 2z cubed minus 2z squared minus 2z minus 3. When I divide that in, okay, that'll get me my complex roots. Now this gets me z squared plus 1, okay, sorry. When you divide that in, you get z squared plus 1. So z squared plus 1 equals 0. These are going to get you your complex roots. So z squared equals minus 1. So z is plus or minus root minus 1, which is plus or minus I. Okay, so z equals plus or minus I. That's question 9. Okay. 13 or 14 are very similar, so I might just do 14, and then you'll be able, because 14 is what I was asked to do, but 13 and 14 are very similar. If you can do 14, you can go back and do 13. So the first root of a complex, so we have z squared minus 4z plus 64 equals 0, and one root, z1, is a plus bi. Is z1 the conjugate also a root? Yes, it always is. Now the book does this a slightly different way, and I will put that up. You can have a look at it, but I think this is fine. So what is the value of z1 plus its conjugate? Well, that's basically saying we're adding the roots. Now if we look here, when we add the roots, we'll get 4. So if I add the roots, the sum of the roots, it's minus the sum of the roots z, always. So that equals 4. The next is, what's the product of the roots? Well, that equals 64. Because remember, a quadratic equation can always be written as minus the sum of the roots at plus the z plus the product of the roots. And then find the equation with the roots a quarter z1 and a quarter of the conjugate. So a quarter z1 plus a quarter of the conjugate is going to be a quarter of the sum. Now the sum was 4, so now we'll get 1. Okay, now a quarter z1 times a quarter z2 is going to get a 16th of z1, not z2, sorry, conjugate of z1. Okay, so a 16th of Z1, Z2 is 64. 16 to 64 is 4. So then we have Z squared minus the sum, 1Z, plus the product, 4 equals to 0. Okay, so if you can do 14, 13 is basically the same.